In the previous video, I have explained what is a greatest integer function and how to find out integral part of a real number. We always consider that rounding down to rounding integer down to the given number. We always rounding down to the integer of given number. Means we always take less than given real number, less than or equal to, which is highest integer. Okay. So once again, I'll write the definition and followed by I will explain a simple properties of greatest integer function. These properties will play a very good role in understanding of like some questions of functions, finding domain, range, and evaluation of limits, and continuity, differentiability of a function, and some evaluation of definite integrals, etc. Well, let us discuss the properties of greatest integer function. F of x equal to integral part of x, as we know that it is represented by square brackets enclosed by x enclosed by square brackets. This is equal to n, where n is an integer, not a natural number, where n is an integer, right? So n less than or equal to x less than n plus 1, and n is an integer. This is the basic definition. What is the other notation of this integral part of x? The other notation is like this. We call it as a floor function. We call it as a floor function. Well, see, we always choose less than or equal to given number. We always choose less than or equal to given number. I'll give you an example. One example. That integral part of you take some e. Okay. Integral part of e. E value is approximately 2.718. So its value is 2 since e lies between 2 and 3. 2 and 3, where e is approximately equal to 2.718. We always consider that only left of the integer 718. Here you see, we consider only left side one, this one. Here we consider only 2. All right, so I can write now the property number 2. That integral part of x is always less than or equal to x. It is always less than or equal to x, but it is more than x minus 1. But it is more than x minus 1. When will you get equal to? When will you get equal to? That I'll write now. Okay. So here you see that integral part of x equal to x. If x is purely an integer, x belongs to z. X belongs to z. There is no decimal part. There is no decimal part. For example, what is integral part of minus 2? Integral part of minus 2 equal to, we just write directly minus 2. Here you remember that output is always an integer. Output is always an integer. Means the range of the function is set of integers. The range of the function is set of integers. This property is very, very important. Second property. We use this property very frequently in evaluation of some kind of limits while using that sandwich theorem. Integral part of x always less than or equal to x, but it is more than x minus 1. Next one, the next property. The next property is, this is the fourth one. Fourth one. What is integral part of some x plus 1? I'll write. Or some x plus 2. Integral part of x plus 2. Here you see. Integral part of x plus some k. Integral part of x plus k equal to. We can bring out k out if we know that k is an integer. K is an integer. Where k is an integer. If k is an integer, then we can write that x integral part of x plus k equal to integral part of x plus k. Right. So, for example, what is integral part of x plus 1? Okay, we can bring out that integer 1 so that we can write integral part of x plus 1. Similarly, integral part of x minus 2. We can write integral part of x minus 2. So these properties are seems to be very simple, but while solving the questions, we have to use them at that particular stage. We have to remember these concepts. Well, so integral part of x plus k equal to integral part of x plus k. Nice. Okay. So if you want a proof of this particular concept, I can prove in only one line. You see that x lies between n and n plus 1. Right? X lies between, assume n and n plus 1. Now adding k is an integer. K is an integer. N plus k less than or equal to x plus k less than n plus k plus 1. All right. Now what is integral part of x plus k? What is integral part of x plus k? As I have said earlier, you always consider that left integer. This is the n integer. Here n belongs to z. Unless otherwise stated, you always consider that n is an integer. So integral part of x plus k now, if you consider this left part, then you can write n plus k. N is nothing but integral part of x plus k. Remember, integral part of x, the term itself says that the output is an integer. Well, so this property is a very good property, and it is good to simplify some large expressions. Coming to next property. Next property is integral part of x. Even if you keep 100 integral parts, it's always equal to integral part of x. Integral part of, I will write, you see, integral part of n. Okay, integral part of n is nothing but n. So therefore, this is equal to integral part of x. X is a real number that always can be written as integer plus decimal part. Integer plus decimal part. We leave the decimal part, we take the integer part. This is the property number 5. Well, so here if you want that what is, for example, here I can write one example, that integral part of 2 plus integral part of x. What is its value? Right? You can write 2 outside. You can write 2 outside plus integral part of x. Nothing but you can write simply 2 plus integral part of x. You give any real number in place of x. Now, one more important property that is very useful. Sixth property. Okay. This is also very useful in proving even odd functions and evaluation of definite integrals, etc. So what is this sixth property? The sixth property is sum of two kinds of integral part of x. That is integral part of x plus integral part of minus x. Integral part of x equal to integral part of minus x. Let us see what will happen. Here we may have two cases. If x is integer, you can write this is 0. If x is an integer. If x belongs to z. Well, for example, see, whenever you get a doubt on certain properties, you always play with numbers. And then you can confirm the real output. So integral part of 2 plus integral part of minus 2 equal to. Integral part of 2 is nothing but 2. Integral part of minus 2 is nothing but minus 2. So we get 0. Now, what will happen if x is not an integer? This is important. This is very, very important. Let me explain through the example so that we can write the generalized thing. Okay. I will take an example. This greatest integer function is very, very difficult when it comes to application. Concept-wise, to understand the basics, very simple. But when we are trying to apply in certain things like number theory or continuity, differentiability, or definite integrals, then we feel, oh, greatest integer function is very difficult, right? Okay, so come here. What is integral part of, if I ask, what is integral part of minus 3.5, right? Remember, minus 3.5 lies between minus 4 and minus 3, right? We always take down to the given real number, you always take integer down to the given real number. So its value is minus 4. This I will write minus 1 minus 3, right? So further I will write minus 1 minus integral part of 3.5. I hope you understand this. Here I wrote with negative minus 3.5. Here I wrote without negative 3.5. But the extra thing is minus 1. Well, so now this is nothing but this is minus 1 minus integral part of x. This is true if x is not an integer. This particular property is a very, very important. Well, so therefore we can write that combinedly what is integral part of x plus integral part of minus x? Integral part of x plus integral part of minus x. This is equal to, okay. It is 0 if x is an integer. Obvious, if x is an integer, then its sum is 0. and its sum is minus 1. Minus 1 if x is not an integer. X is not an integer. Do you want to prove it? Yes, we can prove it. We can prove it. It won't take much time and it's not at all difficult. Everything depends upon only basics of inequalities. Like you see, that integral part of x equal to n. Integral part of x equal to n. By this time, you must get when it will be n. When x lies between n and n plus 1. This time, I am taking that x is not an integer. X is not an integer. All right? Okay. All right. Okay. So here you see, you multiply with the negative sign for this inequality. For this inequality, multiply with the negative sign. Then inequality will be reversed. I'll write here. A less than x less than b. If you multiply by negative sign, inequality will be reversed, or the quantities will be reversed with the negative sign, like this. Okay, so here I'm going to write left side minus n minus 1. All right, and this side you can write this is minus 1 minus n. So what is integral part of minus x? Integral part of minus x. You always consider, as I said, that you always consider only left one. So minus n minus 1. Very simple. It's not at all difficult. Now add together. Add together. So what is integral part of x plus integral part of minus x equal to, you will get minus 1 if x is not an integer. Wow, nice. Nicely we have proved. So integral part of x plus integral part of minus x equal to minus 1. Well, for example, I'll give you an example. Here is an example. Suppose x not equal to n pi by 2. X not equal to n pi by 2. Okay, n is an integer. What is integral part of sin x? Integral part of sin x plus integral part of minus sin x. What is its value? Right? See here, x is not equal to n pi by 2. X is not equal to n pi by 2. What does it mean? X not equal to 0. X not equal to pi by 2. X not equal to pi. X not equal to 3 pi by 2, etc. Actually, at these values, sin x can be 0, 1 or minus 1. So sin x will be 0 when x equal to 0, pi, 2 pi, 3 pi. You can say like n pi. And sin x equal to 1 when x equal to pi by 2, 5 pi by 2, 9 pi by 2, etc. So x not equal to n pi by 2 is nothing but sin x is not an integer. Sin x is not a integer. So its value you can write minus 1 since sin x is not an integer. Does not belong to z when x not equal to n pi by 2. So this is the one important property. Now, I hope at last, or maybe one or two of properties. There is another property that is known as Hermite identity. Hermite identity. Okay, I'll write that property. Okay, I'll take little break. Okay, welcome back to the next property. Here is the an Hermite's identity. This is very important. Questions can be asked based on this concept. What is this Hermite identity? Integral part of x plus integral part of x plus 1 by n plus integral part of x plus 2 by n and so on up to integral part of x plus n by n minus 1 by n is equal to integral part of nx. Of course, here n is an integer. Here n is an integer. Of course, in fact, here it is a natural number. Okay, I'll take natural number. Well, how do we prove it? So before we prove it, let me give one example so that you can keep in your mind. Okay. If I ask one example, I will write in sigma format. I hope you can understand the sigma. One example. What is sigma? Sigma integral part of sum 2 by 3 plus, okay, r by 100, r equal to 0 to up to 99. This is the question. Okay. So you observe. Okay. So if you can by heart this identity, then many questions you can do on fingertips. See, here I have given this is an x value, right? And this 100 is an n value. Done. Good. So using this identity, I can write directly integral part of nx, integral part of nx. So nothing but this is equal to n is nothing but 100, x is nothing but 2 by 3. All right. So this is equal to this is nothing but 66 point. 66 point. I hope 6, isn't it? 6. So integral part of 66.6 equal to you write 66. That's it. Over. Very simple. Well, how to prove it? I will prove in means very easiest way. I hope. I feel that it is easy. I don't know if there is other method. I'll take that difference of these two, LHS and RHS, difference of LHS and RHS. I'll assume some f of x. Proof. Let f of x equal to, let f of x equal to, okay. I'll write in sigma format, sigma integral part of x plus r by n, r equal to 0 to n minus 1 minus integral part of nx, minus integral part of nx. I hope I am not teaching boringly. Maths is a long ways, right? We can talk anything in terms of maths. So here f of x equal to sigma r equal to 0 to n minus 1 x plus r by n. If r 0, you will get first term. If r equal to 1, you will get second term. For r equal to 2, you will get third term and so on. I have just taken difference of LHS and RHS. Nice. For k belongs to z, I am taking an integer k. right? What is f of x plus k? What is f of x plus k? F of x plus k is nothing but in place of x, you write x plus k. In place of x, you write x plus k. Okay, wherever you see x on RHS, everywhere you write x plus k. Okay, I'll write here that sigma r equal to 0 to n minus 1 integral part of x plus k plus r by n minus integral part of n into x plus k. All right. So you please try to remember once again that what is integral part of x plus 1. Integral part of x plus 1. You can bring out that integer from the greatest integer function. That I am going to do now. This is equal to, this is equal to. You can bring out this k outside of this integral part because that is an integer. Sigma r equal to 0 to n minus 1 integral part of x plus r by n, okay, plus k, keeping in bracket. Nice. Minus integral part of this, I'll write nx plus n into k. Remember, n is an integer, k is an integer. Okay. All right. Now, this is an integer. This part as an integer belongs to z. So you can bring it out. You can bring it out. Well, now here this is a constant. You have to add how many times? N times. You have to add n times. So this is equal to sigma r equal to 0 to n minus 1 integral part of x plus r by n, right, plus nk minus integral part of nx. I am bringing out that nk, so minus nk. Here outside minus is there. I hope you are understanding. If you listen carefully, definitely you will understand. So now what will be cancelled out? Nk is a cancelled out. What else left? Should we get that original function or something else? You look at the original one. This is the original one. This is the original one. And same terms appeared here also. Same terms appeared. So this is nothing but f of x. Okay. Therefore, f of x plus k equal to we got f of x. That is, I will write a few things that f of x equal to f of x plus 1 equal to f of x plus 2 equal to f of x plus 2 and so on. If you think for which function the value remains same even after replacing x by anything. If x is replaced by x plus 1, value is same. X is replaced by x plus 2, value is same. X is replaced by x plus 3, value is same. X is replaced by x minus 3, value is same. For which kind of function that value remains same irrespective of x? That is only possible for constant function. That is only possible for constant function. So this implies f of x is constant. Is constant. Right? So therefore, f of x equal to c. It is constant for every x, for all x belongs to. Now I want to find out the value of C. What is C value? This is important. Here I wrote a term that it is true for any x. It is true for any x, right? So I would like to find out the value of C just by putting 0. F of 0 equal to C. Well, f of 0 equal to C. What is f of 0? Have a look on the first term, this one. Here. Put x0 here. Okay. You will get r by n minus 0. You will get sigma integral part of r by n, r equal to 0 to n minus 1 minus integral part of 0 equal to C. Implies we got C equal to 0. Right? So therefore, f of x equal to 0. Which implies that sigma r equal to 0 to n minus 1 integral part of x plus r by n equal to, we got integral part of nx. But I did not explain how that integral part of r by n is 0. How integral part of r by n is 0? Very simple. Here you see r lies between 0 to n minus 1. R lies between 0 to n minus 1. Divide by n. 0 by n. Here n is a natural number. So inequality will not be disturbed. N minus 1 by n implies 0 less than or equal to r by n less than 1 minus 1 by n. So this is less than 1. This is less than 1. So if any quantity lies between 0 to 1, excluding 1, that integral part is 0. That integral part is 0. We always consider that left integer only. This implies integral part of r by n equal to 0. This is what. So the proof is completely finished. If you do not understand, you please watch it again. I hope I felt that I have explained very clearly. I think one more property is left, that is regarding number theory. Like how many integers are there from 1 to 1000 that are divisible by 3, that are divisible by 5, that are divisible by 7, like that. So I hope that property is 9. Property 9. Ninth property. Ninth property. The number of integers, the number of integers from 1 to n, 1 to n, number of integers between from 1 to n that are divisible by m, that are multiples of m are divisible by m. Anything is okay. That are multiples of m. I take that m belongs to n is equal to integral part of n by m. That's equal to integral part of n by m. How many integers are there which are divisible by m from 1 to m? One example, the number of integers from 1 to 1000, 1 to 1000 that are okay divisible by okay. I'll write that part that are divisible by is a common divisible by 1. You say divisible by 3 is integral part of 1000 by 3, right? So this is equal to 3 3 is 9, again 10, 3 3 is 9, again 10, 3 3 is 9, and you leave the decimal part. So there are 333 numbers which are multiples of 3. Similarly, for example, if I ask how many are there divisible by 5, simply 1000 by 5 equal to, you will get 200. And third, for example, divisible by 7 is integral part of 1000 by 7. This is equal to 7 ones, okay, 7, 30, 7 fours, 28, 20, 7 twos, 142. Of course, there are some deeper properties of greatest integer function. All those cannot be covered in one class. So in the next class, I'll explain some more deeper properties of greatest integer function, and I'll solve a few questions of JEE Main and uh, uh, problems related to domain range of functions and limits, continuity, differentiability. So I want to bring all the questions involving greatest integer function under one umbrella. Thank you very much.